Hello everyone, welcome to another lecture as part of our ME 6151 course, Computational Heat and Fluid Flow. So let's get started. So in the previous lecture, we looked at the implementation of higher order schemes, right? Whether on a structured mesh or on an unstructured mesh, essentially using the deferred correction strategy, right? And then we looked at convection diffusion on unstructured non-orthogonal meshes. Essentially, how do we go about solving convection diffusion? We formulated the equations for both the upwind difference scheme as well as the central difference scheme, right? We have also extended or kind of discussed the higher order schemes, right? We extended them to how to solve them on unstructured meshes. For example, both the second order accurate scheme, second order accurate upwind scheme, as well as the quick scheme, right? Both of them we saw how do we extend them to unstructured non-orthogonal meshes. All right. Excuse me. All right, so let's move on. In today's lecture, we're going to complete the discussion on convection because the only thing that is remaining is the boundary conditions for convection. So we're going to look at that. And then that essentially finishes the chapter on convection diffusion. Okay. Then the next chapter is actually on the linear solvers, but most of the linear solvers part we have already discussed, so we will skip that for now and we'll move on to the chapter afterwards, that is the final chapter, that is basically the discretization or the solution of fluid flow equations. So that is the final chapter. So once we finish the fluid flow equations, we'll come back to the linear solvers chapter and finish whatever is remaining there. All right. Okay, so let's move on with the boundary conditions for convection. So let us recall the boundary conditions we have for diffusion were around three types of boundary conditions, right? We said if you have only a diffusion problem, whether it is steady or unsteady, you specify the value of the unknown, that we call it as a Dirichlet boundary condition. If you specify the gradient of the unknown, then we said this is a Neumann boundary condition. And the third type of boundary condition we can have is basically a combination of Dirichlet and Neumann, that is basically A phi plus B partial phi partial n equals some C3 or something, that is basically your mixed boundary condition. Okay, so these are the boundary conditions for if you have only a diffusion problem. Now if we have a convection problem or a convection diffusion problem, then you need to specify few boundary conditions, and those kind of fall into two categories. One of them belongs to the category of flow boundary conditions on the flow boundaries. That means these are the boundaries where the flow can enter the domain or leave the domain. Okay, so this is basically the boundaries where flow enters or leaves the computational domain. Okay, computational domain, and we kind of categorize them as inflow boundaries and outflow boundaries. So we need to see how do we discretize the cells which are sharing a phase on the inflow boundaries or on the outflow boundaries. And we have another type of boundaries that exist, which are known as geometric boundaries. Okay, so these are basically walls. For example, the walls of a duct in which the fluid is flowing. Okay, so these are essentially the geometric boundaries. So we need to see how do we discretize the convection term on those phases which happen to be on the geometric boundaries. Okay, essentially these are the cells which have a phase on one of these boundaries. Okay, so we'll see how do we apply the boundary conditions for these cells here. All right, let us move on then. So let us first start off with inflow boundaries. So inflow boundaries, so let us essentially we have a schematic that is drawn here. This is basically an unstructured mesh. We take this cell, and this vertical line here is an inflow boundary. Okay, so we say this is an inflow boundary. So out of the three phases, two phases are interior phases and this one is a boundary phase. Just like before, we will call it as C0 cell, and the vector connecting the cell centroid C0 to the phase centroid is EXI. And the phase of this boundary phase is basically the area vector is pointing outwards like any other phase. And then we also have UB bar, which is the inflow velocity vector that is pointed towards into the cell. Okay, now if you look at the convection term for this particular phase will have both the convection and the diffusion terms. Now we are looking at the convection term. the convection term would read as del dot rho u bar phi b, right? Now, what needs to be specified on this boundary, on the inflow boundary? What needs to be specified? Essentially, because the flow is coming in, we need to specify essentially everything that we need here, right? Because the flow is coming in, so we need to know what is the density of the fluid that is coming in, with what velocity the fluid is coming in, and what is the scalar that it is bringing in, right? So all these three needs to be known. For example, if you're solving for a convection diffusion equation, then u bar by default is anyway known, right? The flow field is already known, so we need to know, of course, know what is the scalar value that it is bringing, is brought in through the inflow boundary. Okay, so essentially we need to specify. So somebody says if there is an inflow boundary, then the density on the boundary, the velocity vector on the boundary, as well as the phi b, the scalar value on the boundary, all three needs to be specified. Okay, so once we know all these three, of course we can evaluate this term, right? So then how do we call a boundary as an inflow boundary? A boundary will be inflow boundary if the velocity vector is kind of pointed inwards into the domain. So that means ub bar dot ab bar has to be less than or equal to 0. Then only we can call this as an inflow boundary, right? Okay. So far so good. Then let's move on to how do we kind of put these terms back into the equation. So the discrete equation for boundary cell would be, basically you have the diffusion terms, right? We have the interior terms, which are the gamma grad phi f dot af bar, and we have the convection term, that is rho u bar phi f dot af bar. Okay, so these are for the interior faces. That means in the triangular cell here, these are basically the two interior faces. Okay, and then we have not written the boundary face here. So if I write the boundary face here, you have gamma grad phi b dot ab bar minus rho u phi b bar, rho u phi b dot ab bar. So this is the only for the boundary cells. Plus we have the source term, that is SC plus SP phi 0 times delta V not equal to 0. Okay, so this is our original regular equation, but written in terms of kind of separated out in between the interior and the boundary So this is basically written for a boundary cell. Okay, all right. Then what about so we know how to kind of discretize these interior faces already. Now we just need to look at how do we discretize the boundary terms, right? Only thing that needs to be understood is how do we discretize these two terms, right? All right. That means if we look at those two terms, even the first part, which corresponds to the diffusion, is already known to us. We know how to discretize this. This will basically give rise to some coefficient times partial phi partial xi, and some other coefficient times partial phi partial eta if you have an unstructured non-orthogonal mesh. Okay. Now what about the other term? So rho u b bar phi b dot ab bar, in which rho b bar is known, rho b is known, the density at the boundary is known, velocity is known, phi is known, and ab bar is known, right? So we know essentially everything is known to us. So we can just plug it in this value and then evaluate the particular value of this particular term. Okay. Now where will this term go? Because everything is known, this term will have to go into the b term of the equations. Okay. All right. In fact, for that matter, even this will go into the b term, isn't it? Okay. So everything will go into the b term. So that is how we go about implementing inflow boundary conditions for convection diffusion. Okay. Let us now move on to the other boundary condition, which is basically an outflow boundary. Let's say if you have an outflow boundary, that means we call this particular cell as again a cell that shares a face on the outflow. So this vertical line here is the outflow boundary. As before, we have a C0 cell, we have E xi. The velocity vector of the boundary face is the area vector is pointing away, and the velocity vector is also is drawn here such that the flow is leaving from the cell out of the domain. Okay, so on the left hand side here is where we have the domain, and this is the boundary. All right, now when do we call this as an outflow boundary? We can call this as an outflow boundary if your ub bar dot ab bar is what? Is positive, right? So both of them have to be in the same direction. If that's positive, then we can call this as an outflow boundary. If the dot product of ub bar and ab bar is negative, then it is an inflow boundary. Okay. Now what needs to be specified in an outflow boundary? What do we need to specify? Do we know anything? we don't know, we cannot specify anything, because whatever is happening inside has to leave the domain. So the outflow boundary is kind of a boundary where things happening inside needs to be kind of dictate what should actually leave to the outflow, right, depending on the flow rates and things like that. Okay, so essentially we don't know yet what needs to be specified. Essentially we cannot specify anything as of now, because we feel that whatever is kind of computed inside needs to kind of dictate what should leave through the boundary. Okay, what about the terms that correspond to the boundary phase? We can write a similar equation for this particular cell, where we have contribution of the interior phases and contribution of the boundary phase. We will only look at the boundary phase. The boundary phase is basically, you have gamma grad phi b dot ab bar minus rho b ub bar phi b dot ab bar, right? So you have the diffusion part and the convection part. Now for most of the fluid flow problems that we encounter, we assume that the diffusion component is 0. Okay, so we make this assumption. We'll come back to what is the consequence of this assumption. Okay, so we are assuming that there is no diffusion happening in the cell that is sharing a phase on the outflow. Okay, so we are assuming that this is 0. So the only term remaining is the convection term as far as this is concerned. By the way, the diffusion components for corresponding to these two interior phases are still intact. Okay, they are not assumed to be 0. Only the component related to the boundary phase is assumed to be 0. Okay, then we only have the convection term that is remaining, but because we know what is ub dot ab, right, ub bar is known from the flow field, right, because this is a convection diffusion equation. So ub bar is already known. ub bar dot ab bar is positive, we know that. That means the flow rate that we have is positive. Because this is positive, what will be the value for phi b? Because this is positive, if I use an upwind difference scheme, the phi b has to be equal to phi 0, right, if we use an upwind difference scheme. Okay, then we can rewrite this equation as minus rho b ub bar phi b dot ab bar as minus fb times phi naught, right, because fb itself is rho ub bar dot ab bar. So this is basically your now convection term, which is essentially evaluated for an outflow boundary. Okay, now where will this term go? This term has to go into will it go into the b term? No, it will go into the AP term, right, essentially, because you have phi 0. So essentially this has to go into the AP term, or for the C0, the central coefficient, right? Okay. All right, now let us kind of discuss further on this particular assumption that we have made, that the diffusion is neglected for the boundary phase when compared to convection. Okay, so let us look at that. So because we have assumed this to be 0, we don't need to specify the value of phi b, right, on the boundary. In fact, we don't even know what this value of phi b will be, because it has to be dictated from what is going on inside the boundary, right? By making this assumption that the diffusion is 0, what we made is we go back to our cell Peclet number discussion. So we said that the cell Peclet number that we have kind of goes to infinity, because the diffusion, the ratio of convection to the diffusion, and the diffusion we have assumed to be 0 for the local cell Peclet number for the particular phase, then the local cell Peclet number is now tends to infinity, right? That means this is a convection dominated flow, right, where we are assuming that the effects of diffusion are negligible only for the boundary cell, between the boundary cell and the boundary phase. Okay, all right, what does that mean? That means that, let's say, if you have a flow and this flow rate is let's say is quite large, we have a large flow rate, that means the convection is very much dominant. As a result, this phi I that we have, which is the value of phi in the interior, will get convected to the boundary, right? So phi b as a result will take a value of phi I, and phi I would not be affected because of phi b, right? Because of the large flow rate, whatever is happening inside would be dictated by what will happen at the boundary, right, but not the other way around. So for all these cases where the flow rates are kind of considerably large or are significant compared to diffusion, then we can assume that the diffusion component is very small. However, if you realize that the flow rate is very small, and if the diffusion plays a role, then we of course need to specify what is the value of phi b, because the value of phi b would diffuse and affect the value of the cell centroid near the near boundaries for near boundary cells. Okay, so that needs to be accounted for, but otherwise for most of the problems, for the convection dominated problems, whatever is happening inside can be taken to be same as what will happen will be convected downstream, and the diffusion effects between the cell centroid to the face are quite small. Okay, all right. So that is about the implementation of outflow boundary conditions. Now we have the final one more boundary condition, that is basically your geometric boundaries. That means we have walls such as this, in which we have a flow that is going in, and let's say there is a cell here. Okay, we have a cell here, and this is your AB bar. Okay, again pointing away from the cell. Okay. Now at walls, essentially the condition we have is the flow cannot go normal to the face, right? It cannot go in normal to the face. That means the flow is kind of, so the wall is kind of impermeable, right? So for the flow, that means the dot product of the velocity and the area vector, that is UB bar dot AB bar, would be equal to 0, right? So here we have not made any assumption related to the viscosity. We have not made anything related to the no slip condition. Okay, we have not made any assumption, but we are only talking about the impermeability of the wall, which makes it UB bar dot AB bar equal to 0. Okay, so once you have UB bar dot AB bar equal to 0, what will be the flow rate across the wall? That is of course 0. That means if we look at the boundary contribution, then we have the diffusion term and the convection term. Because the flow rate is 0, this term will go to 0, right? And we are only now left with the diffusion component. So this is kind of opposite behavior to what we saw in the context of outflow boundaries, right? Because for outflow boundaries, we said we are neglecting diffusion and the only thing we have is the convection. Whereas for geometric boundaries, we have convection equal to 0 and only thing we have is the diffusion. Okay, so these are two kind of opposite elements. What about the diffusion component? The diffusion terms, we know that again somebody has to specify either it's as a Dirichlet boundary condition or using a Neumann boundary condition or with using a mixed boundary condition, and these can be now evaluated depending on the boundary condition that we already know how to essentially discretize these values, right? We know how to discretize these terms, whether it is a Dirichlet, Neumann or a mixed boundary condition. Okay, so that kind of finishes the chapter on convection diffusion. Okay, so all right, so let us kind of move on to the solution of fluid flow equations. So in fact, if you look at the general scalar transport equation, that is your general scalar transport equation. Okay, basically that is given by partial T of rho phi plus del dot rho u bar phi equals del dot gamma grad phi plus S phi, right? We have now seen each and every component of this equation. We have seen how to solve the diffusion part, the convection part and the unsteady part. So in principle, we can now solve for a convection diffusion equation or a general scalar transport equation for any scalar phi. Okay. Now, if you look at the fluid flow equations, we basically have pretty much a similar structure as compared to the general scalar transport equation. Only thing is that now your phi is replaced with u, right, and v. So instead of one equation, now we have two equations. Let's say if you consider a two-dimensional flow situation, okay, if we consider a two-dimensional flow situation, then you have, instead of one equation, we have two equations, one for the x momentum equation, the other one for the y momentum equation, in which phi is replaced with u or v. Okay, of course we also have continuity equation in addition to these two equations. Okay, so if we compare, what we have is the first term is partial T rho u plus del dot rho u bar u, right? Excuse me. So we have phi replaced with u, and then del dot gamma replaced with mu. Instead of grad phi, we have grad u plus su minus partial p partial x. Now this is the term which is extra here, right, as compared to what we have in the general scalar transport equation. Okay, so this pressure gradient term is something that is extra. which we need to see how do we do it, how do we evaluate this. But otherwise this looks very similar to the general scalar transport equation. Of course, we also realize that the term that we have here, this is basically your SU, right? This is, we have written it as source, but this contains what? This contains the not only the body force term, right, but also it contains all other the miscellaneous derivatives that were coming out, which were kind of not written here, right? It contains several velocity gradient terms as well. Now we know that if we assume a constant viscosity, right, if we assume a constant viscosity and if we assume the flow to be incompressible, then we know that SC will have only the body force component, because every other term, the miscellaneous derivatives of velocity gradients, would all go to zero, right? They will all go to zero because of the conservation of mass equation. Okay, so we realize that. All right, but anyway, those will not cause an issue in terms of the solution algorithm, whether we have constant viscosity or not. It doesn't matter. We can still go ahead with the calculation of the source term by incorporating both the body force and all of the miscellaneous velocity gradient terms. Okay. All right. So how do we now discretize the momentum equation? So we would like to get started with a steady momentum equation. Okay, we don't want to do the unsteady as of now. So let us make some approximations. The approximations we make are basically the flow is steady and it is also incompressible, and the fluid we assume is basically a Newtonian fluid. That means whose shear stresses are proportional to the strain rates. Okay. So we make these assumptions and then go ahead with the solution of the fluid flow equations. We also assume to begin with a uniform or a structured mesh, okay, which is basically given by our regular Cartesian mesh. Basically that is cell P, and we have east and west cells and the north and the south cells, okay, and the width of the cell P for which we want to write the discrete equations is basically given by delta x times delta y. Okay. Then what are the equations we have? If we consider steady flow, we don't have the dou partial rho u by partial t term is gone. So only thing is we have the convection term, that is del dot rho u bar u equals the diffusion term is del dot mu grad u plus su minus we have essentially minus dp dx, right, minus partial p partial x. That I have written it as in terms of grad p. We can write it as minus I dot grad p, right? This is basically evaluates to partial p partial x. Similarly, the y momentum equation is basically del dot rho u bar v equals del dot mu grad v plus sv minus j dot grad p. Okay, so that's your y momentum equation, which is basically minus partial p partial y. Okay. Now we realize that the SU and SV do not just contain the body force terms; they also contain all the miscellaneous velocity gradient terms, which we did not write in the viscous terms here. Okay. And depending on the value of the viscosity we take, all other terms would actually go to zero as well. That possibility is also there. All right. Let us move on then. Then if we want to apply finite volume method to these two equations, we know that we can solve for these just like the way we have done before. So we know how to apply the finite volume method for the convection term and for the diffusion term and for the source terms. Only thing we don't know or we haven't done is basically the pressure gradient term. So let us look at only this term, apply finite volume method for this, and then plug it back into this equation and write the complete general discrete equation afterwards. Okay, so we are only focusing right now on the grad p term. So if we were to apply finite volume method, the first step is to integrate it on a control volume. So if we take delta v is the volume of the cell P, so this will be integral delta v grad p dv, right? Again, invoking Gauss divergence theorem, we can write this as integral over the control surface p dA bar. Okay, that equals, assuming that the pressure on the faces is constant and the cell centroid value or the face centroid value can be used to represent that pressure on the face, then if this is p little e, this is p little w, and similarly p little north and p little south, then we can write this as a summation of all the faces east, west, north, south, pf times af bar. That is the pressure on the each of the faces times the af bar. Okay. Now if we go back to the x momentum equation, then what we have is we have not just grad p, we have minus I dot grad p. So that means whatever we got here, we need to take a dot product with minus I. Okay. So that means going back to the x momentum equation, the term we have is minus I dot grad p dv integral del v. This is basically minus I dot summation f p of af bar. Okay, where f is east, west, north, south. Okay. Now what about af bar? What are the values for area vectors for faces? We know that a little east equals delta y I cap. A west would be minus delta y I cap. A north would be delta x j cap, and a south would be minus delta x j cap. Okay. So essentially, if we take a dot product with minus I, only terms that survive out of this equation are the east and west, because the north and south contain j cap quantities, which will give you 0 when you take a dot product with I hat, right? That means only thing survives is basically the east and west terms. So we have minus p east ae bar dotted with I minus p west aw bar dotted with I. Ae bar dotted with I is basically delta y. Aw bar dotted with I is your minus delta y, so it basically makes it this as a positive. So what we have is delta y times p west minus p east. Okay. So that is how you get for the pressure gradient term in the x momentum equation. It the discrete value reads as p little w minus p little e times delta y. Okay. That means the value of the pressure on the faces, pw minus pe times delta y, is the evaluation of this particular quantity, the pressure gradient coming up in the x momentum equation. Alright, then let us look at the y momentum equation. So the y momentum equation has minus j dot, this is not correct, this should be a gradient, this is grad p, right? So this should be a grad here. Okay, so this is basically grad p dv. That means which, if you apply Gauss-Divergence theorem, this will come to minus j hat dotted with sigma p of af bar. Okay, and again all the faces are east, west, and north and south. Okay, again we realize that because we are taking a inner product with j cap, only terms that survive here are the north and south, because they are the ones which have j cap with them. That means we get minus pn times an bar dot j cap minus ps times as bar dot j cap. Okay. So as is basically your minus delta x j cap, and this is delta x j cap. As a result, this will be ps minus p north times delta x. Okay. So where pressure on the south face minus pressure on the north face times delta x is what we get. Alright, that kind of completes the discretization of the x and y momentum equations, the pressure terms, the pressure gradient terms that we get. And we are now in a position to kind of write down the discrete equations. So if we start off, the steady Newtonian incompressible flow equations are given here, which is del dot rho u bar u equals del dot mu grad u minus I dot grad p plus su, and the other one is del dot rho u bar v equals del dot mu grad v minus j dot grad p plus sv, right? So if we plan to apply finite volume method for this, then just like the way we have done it for the general scalar transport equation, we can write the final discrete equation as AP phi p equals sigma nb phi nb plus b, right? Similarly, because the quantity here we are solving for is u, so we can write this as AP up equals, right, sigma a and b phi and b, that is basically sigma a and b u and b plus b. Okay, so we have this quantity, and then plus the pressure gradient term here would reflect to something like this, which is basically pw minus p little e times delta y. So we got basically this is now our extra term, right? So basically this is our extra term as compared to the general scalar transport equation. Okay. Similarly, the y momentum equation can be written in the discrete counterpart as APVP equals sigma a and b v and b plus bv coming from the source term, plus we have for the pressure gradient we get ps minus p naught times delta x. Okay. Now remember that these are basically evaluated on the faces, so these are the phase values. Okay. All right. Now of course, can we solve for these equations 1 and 2? we cannot solve for them as it is, because these are two equations and the unknowns are three, right? Because your UP, UV and pressure 3, there are three unknowns, but these are only two equations. What is the third equation? The third equation is what we have not written down here, is the continuity equation. Okay, so essentially in principle you have three equations and three unknowns, so we can possibly solve for this thing. But if somebody gives you a pressure field, if the pressure field is known, then these two equations can be solved, right? If the pressure field is known, then it's a matter of calculating, putting it back here and calculate from the first and second equation the u and v velocity fields. Okay, so now remember that up till now, when we had the general scalar transport equation, our u was known, right? It was a known field. But whereas here in the fluid flow equations, the u bar, the velocity field itself, is unknown, right? And also the pressure field itself is unknown. Okay, that's what we are trying to solve from the given boundary conditions for the domain that we identify. Okay, now because pressure at the faces is required, we don't know these values, because pressure is assumed to be stored at the cell centers. So we need a profile assumption for pressure. So if we assume that the pressure varies linearly and we assume a uniform grid, then the pressure on the east face can be written as P capital E plus Pp by 2. Similarly, P little w would be written as P capital W plus Vp by 2, and P on the north face can be written as P capital N plus Pp by 2, and P on the south face can be written as P south plus Pp by 2. Okay, so we essentially made a arithmetic average. If we substitute these back into the this equation, then what we get is, because Pp comes up in both equations and there is a minus here, we end up with P capital W minus P east times delta y for the pressure gradient term in the x momentum equation, and for the y momentum equation we end up with P south minus P north times delta x. So this is P capital S minus P capital N times delta x. Okay, alright, so now we kind of translated the pressure gradient terms into cell pressures. Okay, from the phase pressures to cell pressures is what we have done. So these are now in terms of cell pressure values. Okay, so essentially if we know the pressure field, that is we know the Pxy, somebody gives us, then we can use the equations above and of course calculate for the velocity field. Okay, but the pressure field itself is an unknown, and the only equation that we have at our disposal is the continuity equation. Okay, so the continuity equation is the only one that we have remaining, using which we hope to obtain the pressure field. However, we realize that the continuity equation is not an equation for pressure. Okay, so that is the first difficulty. So this is difficulty 1, is basically we have three equations and three unknowns. However, the first equation is the x momentum equation, is an equation for u, the y momentum is an equation for v, whereas the equation for pressure is missing, because the continuity equation is also in terms of velocities but not in terms of pressure. Okay, so this is the first difficulty we encounter when we try to solve fluid flow equations for incompressible flow. Okay, because you remember, if the flow is compressible, then we know that there is also an extra thing, that is basically your density comes into play, and it through the equation of state, the density and pressure are related. As a result, things will be little more are actually balanced, right? Which is not the case for incompressible flows, because density is now constant. Okay, so that is the first difficulty. We will see what are the difficulties we will get in order to solve the fluid flow equations for the incompressible range. Okay, then let us look at the discrete continuity equation. So the continuity equation is basically partial rho partial t plus del dot rho u bar equal to 0. Because we are assuming steady flow, this particular term here is assumed to be, this is basically goes to 0, so we don't have dou rho by dou t. So only thing we have is del dot rho u bar equal to 0. Okay, so if we apply finite volume method, again we integrate this on the cell P, that is integrate delta V. This is integrated on cell P. Okay, so del dot rho u bar dV equals 0. That means equals integral control surface applying invoking Gauss divergence theorem. We can write this as rho u bar dot dA. Again, assuming that rho u bar can be represented using the phase value, and that is phase centroid value is a representative for the entire phase. We can write this as rho u bar f dot AF bar. Okay, so basically you have all the four phases, east, west, north, south, and this quantity would be equal to, this is basically equal to 0. That is your discrete continuity equation. Okay, now we have 4 phases, so we can expand this. AF bar is known, A east, A west is basically known, similarly A north, A south. So this can be expanded, and what we get is, you get rho u east delta y minus rho u w delta y, because AW is minus I cap delta y, and similarly rho Vn delta x minus rho Vs delta x. This is nothing but, if you go back to the convection discussion, this is nothing but F east minus F west plus F north minus F south, right? So this is basically conservation of mass or continuity equation. This should be equal to 0, right? So this is your discrete continuity equation, right, in terms of the phase velocities. The velocities are now u little e, u little w, v little n, and v little south, which of course are not available, right, because we have not been storing velocities at the phases. We have been only storing velocities at the cell centroids. That is, velocity is only available at cell P centroid, E, W, N, and S, all capital letters here. So if we assume a uniform grid for the sake of simplicity, then we can write again using linear interpolation rho u E as density is anyway constant, so this we can write it as rho u P plus rho u capital E by 2. Okay, similarly rho u little w as rho u capital W plus rho u capital P upon 2, and similarly rho v n can be written as rho v P plus rho v capital N upon 2, and rho v south can be written as rho v capital S plus rho v capital P upon 2. Okay, so we have all these 4 values which we can substitute back here, and as you can see, again similar to the pressure case, the rho u P gets cancelled with the rho u P here because we have a east minus west, so this gets cancelled. As a result, we get rho u capital E delta y, right? So discrete continuity equation for cell P would read as rho u capital E delta y minus rho u capital W delta y plus rho v capital N delta x minus rho v capital S delta x. Okay, so this is your now discrete continuity equation for cell P. Okay, now what we see here is that this is surprising because we have written an equation for cell P and none of the values of UP or VP which correspond to the cell P feature in the above equation. So this equation is an equation for cell P, but the values of that particular cell are not there in the equation. Okay, so that is something has very strong implications. Okay, so we will see what implication does it have because of this thing. Okay, so essentially because of the UPVP not featuring in the above equation, we'll see that there is a major consequence of that. A major trouble is kind of coming, okay, in the process of the solution procedure. Okay, all right. That means this kind of equation, because your UPVP do not feature in the equation, this can actually support a checkerboarded kind of velocity pattern. For example, if U east and UW are of the same value, however they are different from the value of UP. Okay, so if U east equals UW, however they are, that is not equal to UP values. Okay, similarly Vn equals V south, but they are not equal to Vp, then this equation can still be satisfied, although there are oscillations in the velocity field. This equation will still give you a conserved continuity equation. What that means is that basically this kind of an equation supports checkerboarding, right? So for example, if you see, this is basically, these are different cells. Okay, each of the colors here is a cell. So what we have is basically this is a particular cell. Okay, U equal to 30 is a cell. Similarly, yeah, this is the grid. I think the grid is quite light here, you cannot see. Okay, so that means let's say if this is your P cell. Okay, P cell has U equals 30. However, as you can see from this equation, only U east and UW matter. So this is 10 and this is 10. So this 10 minus this 10, that satisfies. Similarly, V north and V south would be 20-20. So as a result, this gives you perfect conservation of mass for this kind of a checkerboarded velocity, right? Although we know that the velocity itself in the U and V components, there are oscillations, right? There is a kind of a chessboard or a checkerboard kind of pattern existing, which is satisfied by this kind of a continuity equation. Okay, but okay, but we also know that we are not just solving for the continuity equation, right? So if continuity equation supports this kind of thing, let it be, because we have the other equations which are the momentum equations. What about the momentum equation for u and v? They may not support this kind of a checkerboarded velocity pattern. As a result, this will be thrown out at some point in the solution procedure. However, okay, but if the momentum equation for some reason sustains this pattern, right, then this will be contained, this will be there in the final solution as well. Okay, so because this is supported by continuity equation, and if the momentum equation sustain this pattern for some reason, then the final u and v will contain checkerboarding. We don't want checkerboarding because that is not something that is physical. Okay, we don't want these kind of oscillations prevailing in the solution, and still our solution kind of converges to some value. Okay, but we also recall that the pressure field itself is an unknown, right? Pressure field is an unknown, and if we go back to the kind of the x momentum equation, we know that the discrete equation is APUP equals sigma n bu and b plus bu plus P west minus P east times delta y. Okay, so what we see here is that the pressure difference term, the pressure gradient term, also this also does not contain PP, right? Although this is an equation for cell P, PP value doesn't feature here. That means this also seems like it will support a checkerboarded pressure, right? In which case, if you have PW equal to PE, this would give you a zero pressure gradient, right? Which is not true, because PW equals PE, but neither of them would be equal to PP. Okay, so that means if you have so with such a pressure discretization, it is possible to arrive at a pressure field such that the gradient of P, that is this term, in the momentum equations might cancel out the effect that is coming because of the velocities itself, okay, because of the u and b's. As a result, the velocity checkerboarding could be sustained by the momentum equation as well. Okay, so what we're talking about is basically you have the pressure field. The pressure field might have a checkerboarded pattern like this. Essentially, we have P equal to 5, P equal to 10, P equal to 5, P equal to 10 and 5 and so on. So essentially we have oscillatory field, which will be seen by the x momentum equation as what? As a zero gradient pressure field, because if you look at particular P, this is 5 minus 5. So this would be basically zero pressure gradient. So this is a zero pressure gradient. As a result, you would see that this momentum equation cannot see this pressure gradient. Okay, so such a pressure checkerboarding is now not seen by the velocity, by the momentum equation. Okay, similarly, there could be some pattern of pressure field which might cancel out those pressure gradients here, might cancel out a velocity field like this. That means this negated with a pressure checkerboarding could give you a free run for your velocity and the pressure field, such that they contain this kind of an oscillatory field in the final solution. Okay, do you see that? So the pressure oscillations could, the gradient of which could cancel out the velocity checkerboarding, which will in turn sustain the checkerboarded velocity field, not only in the continuity equation but also in the momentum equations, because now your pressure field might support it. Okay, so you may get such a pressure gradient field which might cancel out the velocity checkerboarding. Okay, as a result, if this happens, usually if this happens when you try to solve it, and as a result the oscillatory essentially your final solution will have wiggles in the velocities and pressures, and these wiggles will manifest themselves into the divergence of the solution. Okay, so that means what we have seen is the oscillatory pressure field will be perceived by x momentum equation as uniform pressure field, right? The gradient of P is 0. Now there could be some other pressure field which might cancel out the effects created by a checkerboarded velocity field, okay, which might basically help sustain this checkerboarded velocity field through the momentum equation as well as, of course, through the continuity equations. Okay, as a result, there might be some wiggles that might start showing up. These are the wiggles, okay, in the pressure and the velocities, which would eventually cause divergence in the solution, these kind of an oscillatory behavior. And that is exactly what happens when you try to solve it the incompressible fluid flow equations when you store all the velocities and pressures at the cell centroids. Okay, so this is the second difficulty, that is basically the pressure and velocity get kind of get coupled, and in a sense they kind of support this kind of a checkerboarded patterns in velocities and pressures, which will manifest into divergence of the solution eventually. Okay, so this is the second difficulty. The first difficulty we saw was that there is no equation for pressure. The second difficulty is that the pressure and velocity, because of their coupling, they may together they may support a checkerboarded velocity and pressure patterns in the final solution. Okay, so that is the other difficulty. So we will see how to address these two difficulties when we try to solve fluid flow equations through some algorithms, okay, that are there in the literature. So that will be our topic for another lecture on another day. Okay, so I'm going to stop here. If you have any questions, let me know through email. All right, talk to you in the next lecture. Thank you.